Okay, I think it's time to start the session. So thank you to come to this session, and this is the track 3, trusted hardware, and we have 3 great paper, and I hope you guys will enjoy it. And one important thing here is, after the talk, if you want to ask any question, and please come here, use microphone. And I know this sounds weird because this is a small room, right? And you can stand out and you can shout out so everyone can hear. But I think the problem here is, we are taped. We are taped. Everything is recorded. So you come here, use a microphone, so you can be recorded. So that's the whole idea. Make sure, if you want to ask a question, come here and keep your question on record. Does this make sense? That makes sense, right? If you're scared, you want your question off the record, of course, you can shout out. But in this case, I think the presenter had a right not to answer your question. Okay, let's start. So the first paper is Hacking in Darkness, Return-Oriented Programming Against the Secure Enclave. It will be presented by Jaehyuk from KAIST. Let's welcome the speaker.
Good morning, everybody. Today I'm going to talk about how to exploit Enclave when it has memory vulnerabilities. We started this work with the Georgia attack from the beginning, and we got a lot of advice in common from the Microsoft research. I'm presenter Jaehyuk. Let's get started. Nowadays, a lot of commercial companies uses cloud services to process users' data, such as transactions, social network service data, or even genomic data. Therefore, confidentiality and integrity of the data processed in the cloud has been becoming more important. However, unfortunately, a lot of commercial companies uses the public cloud services, and it could be vulnerable to data breach attack. To cut the Gordian knot, Intel has recently published SGX. It provides isolated container called Enclave, and it provides security, confidentiality, and integrity guarantee to the code and data running inside the Enclave. Also, these security guarantees are solely provided by the CPU package. Therefore, even the system software are compromised, attacker can never access the Enclave contents. Let me give you how the Intel SGX provides the security guarantees to the Enclave. Basically, all the memory contents of the Enclave are stored in the physical memory by the encryptions. In this procedure, memory encryption engine called MEE encrypts and decrypts all the contents of the Enclave using the hardware-provided key. Therefore, callback attacks and snooping is prevented with the encryptions. Also, to protect the Enclave from the internal software attack, the memory management unit keeps system software from accessing the Enclaves. And it also allows the accessibility of the Enclave to its own contents. Therefore, one Enclave cannot access the other Enclave's pages. Now, under the security guarantees, can we say all the software is secure when we use this Intel SGX? Unfortunately not. As shown in the table, the software vulnerability has been a real threat for many years, and a lot of notorious bugs such as get address info, heartbleed bug, and ghost bug, and etc. has been being recently reported. And the Enclave cannot also be free from the software vulnerabilities. Then, how can we exploit the vulnerability inside the Enclave? Before I give you the detail, let me briefly go over how the return-oriented programming works against the traditional programs. When the attacker doesn't have capability to inject the code into the program, attacker uses the code snippet called Gadgets. To do that, attacker first hijacks the control flow of the program. As shown in the code, the vulnerable mem copy allows the attacker to override a return address stored in the stack. Now let's assume that the attacker wants to invoke the system function to get the shell. To do that, first chain the pop RDI return gadget together with the bin share arguments. By returning to the pop RDI return gadget, it will set the bin share argument to the RDI register. After that, if it turns to the system function, then attacker can get the shell. However, the assumption is the address of the pop gadget and functions are known by doing some reverse engineering. Then what about the enclaves? Basically, operating system loads the enclave pages to memory So if the operating system is compromised, then OS can see the contents of the enclave binaries. So to prevent the reverse engineering and to provide strong security guarantees to the enclaves, in SGX, software vendor can make use of full encryption over the enclave binaries. And VC3 first showed that deploying a private code into the enclave is feasible. Let me briefly go over how to deploy the private code into the enclave. First, it loads the public loader to the enclave, and then establishes a secure channel between the remote solver. And then receives the encrypted code and key from the solver, and decrypt it, and load a private code. And then by deleting the public loader, all the information of the enclave can be completely hidden to the outside, and it becomes a complete black box. Then, can we use the ROP attack against the enclave in the same way? Fortunately, the location of the pop gadget and function addresses may not be known to the attacker, because all the runtime information can be hidden to the attackers. Therefore, even though the attacker can hijack the control flow, he cannot jump to any useful function addresses or gadgets. Therefore, it makes the program just crash. However, the good news is attacker has a lot of capabilities. So, what is the capability in our dark web attack? We assume that the attacker has a full control over the software of the system, including the operating system and the untrusted app that loads the enclave. And we also assume the attacker can make the enclave program crash as many as possible, and to inspect the program, the behavior from the crash. And we also assume that the application is built with the standard compiler with the Intel SDK, and enclave application is distributed in the encrypted format. So our question was, now are we safe? And our answer is no. Under the security guarantees, we demonstrated that we can find a pop gadgets and some function addresses in the darkness. And by using this handful of gadgets, we can completely disarm the security guarantees of the SGX. So let me explain how dark web works. We have 4 steps to find a location of the gadget inside the enclave without any information of the gadget, without any information of the enclave binaries. At the first step, we'll find a location of the pop gadgets. Here, the pop gadget means the gadget that consists of a bunch of pops followed by return instructions. For example, pop once, return, and another example is pop once, pop twice, and return. So using this gadget, we can load the value into the register in the enclave context. After we find all pop gadgets, we will locate an EnCLU and pop RAX return gadget one by one. Here, the EnCLU instruction is used to decipher the pop gadget that we found at the first step, and we can use this instruction to retrieve the sealing key for unsealing, and we can also generate malicious report data to bypass the remote attestations. So, after we find an ENCLU instruction, we can use this instruction to decipher all pop gadgets. Here, deciphering means discerning which gadget loads value to which register. For example, we want to know the information about that gadget pops to RAX register. After we decipher all the pop gadgets, we can find a memcopy functions. And after that, we can copy secret data from the enclave to untrusted memory or inject the malicious data to the enclave memories. So the first step is looking for pop gadget. Even though the attacker doesn't know the content of the enclave memory, the memory layout of the enclave are known to the attackers, because the operating system manages the page permission bits. Also, when the enclave raises the exception during its execution, it throws the exception to the operating system and exits from the enclaves. It's called a Synchronous Enclave Exit, AEX. However, before the exception is delivered to the operating system, the CPU deliberately fills synthetic state to the register file in order to conceal the exact context of the enclave. For example, the RAX register will be changed to 0x3 to indicate the AEX happens, and our DX register will be clear, and the lowest 12 bits of the CR2 register will be clear. However, we can get some partial information from that, and we can know which page incurs the fault. So by relying on these 2 facts, we can find a location of the pop gadget inside the enclaves. First, we push the address that we want to probe into the stack. After that, we push again separate page align addresses into the stack. Here, the key idea is the page align addresses points to non-executable pages, and by returning to one of these non-executable addresses, produces a page fault and AEX. And by inspecting the CR2 register, we can know which page incurs the fault, and from that, we can know how many pops happen before the return instruction is executed. Let's take one example. Let's assume that the probing address does not contain any pop instruction. Then we can know the program behavior. For example, if we raise the segmentation fault at the enclave code section, or just program hangs. However, if the probing address contains more than one pop instruction, it will raise the segmentation fault at one of the page align address that we push into the stack. Let's take one example. Let's assume that the probing address contains one pop instruction and return. Here, we don't know which register is changed by this gadget. We do know that it consumes one entry from the stack and returns to the next address. However, the address is non-executable address, so it will raise the segmentation fault at that address. An attacker can know that the probing address contains one pop instruction and return instruction by inspecting the CR2 register. Now, let's take another example. Let's assume that the probing address contains 3 pop instruction and return. It will anyway consume 3 entries from the stack and return to the next address. And once again, this address is non-executable, so it will raise a segmentation fault at that address. An attacker can know that probing address contains 3 consecutive pop instruction and return instructions. So, relying on these techniques, we can search entire enclave address by increasing the probing address one by one. So as a result of it, we can have a catalog of pop gadgets that shows the address and the number of pop instruction that address have. However, we still need to find a target register. It means that we need an information about which gadget manipulates which register in which order. To do that, we use the ENCLU instruction. Here, the ENCLU instruction handles all user-level operations of the enclave. For example, to retrieve a cryptographic key inside the enclave, it can invoke the EGET key through the ENCLU instruction. And also, to synchronously exit from an enclave, it can also invoke the EExit through the ENCLU instruction. So, ENCLU's behaviors depends on the RAX register value. To be specific, to invoke the EExit instruction, we first load the DirectX4 into the RAX and then invoke ENCLU. Then ENCLU instruction will invoke EExit. And EExit, we use the fact that the exit doesn't erase the enclave context after the exit, and I will explain it at the step 3. So then, how can we find an ENCLU instruction in the darkness? Because ENCLU instruction is used to exit from the enclave, it is always required inside the enclave. So we can assume that ENCLU instruction exists inside the enclave, but we do not know where is it. So to find an ENCLU instruction, we first chain the multiple pop gadgets that we found at the first step, together with the value DirectX4, which is the index of the EExit, and chain the probing address at the last. If pop gadget loads DirectX4 into the RAX and ENCLU at probing address, then it will invoke the EExit. Then how can we know if EExit is invoked or not? If EExit happens, it will jump to address pointed to by the RBX register. So if the gadget chains contains the pop RAX return and pop RBX return gadget, then it will return to the pop RBX address. In this case, RBX register points to the address DirectX4, and this address is unmapped address, so it will raise the segmentation fault at that address. So by inspecting the CR2 register again, we can know that EExit happens and ENCLU's location as well. After we find an ENCLU instruction, we can also find the pop RAX return gadgets. To find a pop RAX return gadget, we use the fact that the RAX register will be changed depending on the exit conditions. When the asynchronous exit happens, the RAX register will be changed to 0x3, and when the EExit happens, the RAX register will be changed to 0x4. So by chaining gadgets one by one and checking the EExit happens, we can find a pop RAX return gadgets. Let's take one example. We first chain the two gadgets together with the value 0x4 and return to EnCLU. If we reach segmentation fault and the value was 0x3 in RAX, then it means a synchronous enclave exit happens. So we chain one more gadget together with the value 0x4 and then return to EnCLU once again. If we reach segmentation fault and RAX register will become 0x4, it means EExit happens. So from that, we can know the lost gadget was pop RAX return gadgets. Then, how can we decipher all the pop gadgets using this step? In this step, the answer is EExit instruction. Compare with the asynchronous enclave exit (AEx), when the EExit happens, all the register contexts remain. So attacker can see enclave register value outside of the enclave. So by using this fact, attacker can know the exact context of the enclave by chaining the EExit gadget at the last. So let's take example. We first pick the one gadget that popped twice, together with the value 0x1 and 0x2. And we return to the EExit gadget. If EExit is invoked, we compare the register file with the value that we push into the stack, that are 0x1 and 0x2. From this result, we can know that the probing address, the gadget, consists of the pop RSI and pop RDI return instructions. So using the same techniques, we can decipher all the pop gadgets that we found at the first step. After we decipher the pop gadgets, we can find a memcopy function using this handful of gadgets. To search the memcopy function inside the enclave, we first change the gadget that pop RDI, pop RSI, pop RDX, and return. Here, we set the RDI register as untrusted memory address. And RDI register means the destination address of the memcopy. And we probe entire enclave code section in the hope that memcopy will be invoked. If the memcopy is invoked, then the destination address located in the untrusted application side will be changed. So from this side effect, we can know the memcopy is invoked. To prove that our attack is feasible, we found all the gadgets from the binary that is compiled with the Intel SDK, and as shown in the left side of the table, we can find all gadgets from the libsgx_trts library, which should be included in the enclave binary when we compile it with the Intel SDK. Also, interestingly, as shown in the right side of the table, some function introduced by Intel pop all the register at the function app below because it doesn't follow the calling conventions. So what can we do with all this? We can first leak sensitive information from the enclave, and we can also even unseal the sealed data. And we can also permanently parasite to the enclave program. So let me show you some case studies. The first case study is dumping confidential data from the enclave to untrusted app. To do that, we first chain the gadget for invoking memcopy. So by invoking vulnerable function, we chain the gadget for memcopy, and returning to memcopy gadget, we can copy entire enclave contents from the trusted app to untrusted app. And we can also compromise the sealed data. To seal the data, we need a key that used to encrypt the sealed data. To retrieve a key, we need to invoke the EGET key instruction inside the enclave. And EGET key instruction can be invoked through the EnCLU instruction. So we chain the gadgets and return to EnCLU gadget. Then it will invoke the EGET key, and sealing key is generated. So after that, by training the memcopy function, we can leak the sealing key, and we can unseal the sealed data. So the second case study is hijacking remote attestation. When the remote server challenges the enclave, our emulated attestation, our emulated enclave first generate a Diffie-Hellman key. And using this malicious Diffie-Hellman key, we can generate a report data. And we inject this report data into the enclave using the memcopy gadgets. And then, to generate a report data that is used to accomplish the remote attestation, we chain the gadget and return to EnCLU gadget. It's because report instruction can also be invoked through the EnCLU instructions. So we chain the gadget and return to EnCLU gadget. We can generate a report data structure. And by chaining the memcopy gadget, we can leak the report data from the enclave to untrusted app. And using this malicious report, we can hijack the remote attestations. So the conclusion is we showed a first practical web attack on real SGX hardware by exploiting a memory corruption vulnerabilities. And we demonstrate how the security of SGX can be disarmed. And we also would like to encourage the community to develop an efficient way to reduce the TCP in an enclave. Let me show you a quick demo. And in our demo, we assume that we use the target binary from the Intel SDK, that is the remote attestation example, and we introduce the Stack Overflow vulnerability. Okay. At the first step, we find the all location of the pop gadgets. So here, the pop gadget 0 means the gadget that doesn't pop, and that address is the location of the pop gadget 0. So we probe entire enclave address spaces and find the all location of the pop gadgets. And to help you understanding our attack, we attach the GDB and check the result. These addresses means the gadget addresses that pop 4 times. So we attach the GDB and check the result. After we find all pop gadgets, we can find the EnCLU gadget by chaining the multiple pop gadgets that we found at the first step together with the value DREX4. And we probe entire enclave address space in the hope that EExit will be invoked. If EExit is invoked, we can know the location of the EnCLU instruction. And we also attach the GDB and check the result. Here, this address means the OP code of the EnCLU instructions. This one. So after that, we find the pop or EX return gadgets by chaining the gadgets one by one together with the DREX4. And we can find the pop or EX return gadgets. So to decipher the pop or EX return gadget, we put some magic value, DREX.bif, and show that each register is changed like this. And as shown in here, the pop or EX return gadget exists in that address. Here. So we decipher all the pop gadgets using the same techniques. And this number means that all the pop gadgets that we found at the first step. So it means that we found that 13,000 gadgets that pop once, etc. And after we decipher all the pop gadget using this gadget that pops RSI, RDI, and RDX or CX, we can set the memcopy function's arguments. So after that, we prop the entire enclave code sections with the hope that memcopy is invoked. So if the memcopy is invoked inside the enclave, it will copy the enclave contents from the enclave to untrusted app. And as shown in here, we can successfully extract the enclave binaries from the enclave to untrusted app. So let's check if it's really a memcopy gadget or not using the GDB. As shown in here, this is the rear memcopy function. Oops. So this is the end of my talk. Thanks for attending. Do you have any questions?
Time for a few questions.
Yuechang from Baidu X Lab. Can you talk about the countermeasure, the possible countermeasures?
Yes. There's some countermeasures. First one is we can modify the EExit instruction to make them not to leak the enclave context, because using the EExit instruction, we can separate all the pop gadgets we found at the first step. So if we can modify the EExit instruction behavior, then we can mitigate this kind of attacks. Also, we can apply other traditional software mitigations into the enclaves. Right. That could be mitigation for these attacks.
Do you think enclave using the type-safe languages is a possible solution? Like
you mean the applying the type-safe language to the enclaves?
Yeah.
I didn't think about that. We can talk maybe offline.
Okay, thanks.
Shuai Wang from Penn State. I'm wondering, have you ever considered some other calling convention? For example, the 32-bit calling convention.
You mean the gadget that I found in here?
Yeah, because, for example, you assume the first parameter is in the RDI register, but that's only valid in the 64-bit calling convention.
So you mean how can we do the same things in the 32 bits?
Right.
Okay. We can do easily. We can more easily attack the 32-bit enclaves.
Yeah, but how you organize the parameters, because they are passed on the stack.
Right.
So
then we can just override a stack.
Okay. So you must have found some push, right? OP code, right?
Excuse me.
It only the pop does not work, right? You must have found some push, right? Anyway, we can talk.
Yeah, we can talk later.
Thank you. Very nice talk.
Thank you.
Nathan Downhun from UPenn. Great talk, really cool work.
Thanks.
I really like the leakage channels, and I'm wondering, you answered a question about, what can we do to mitigate, and I can see this nice arms race of ASLR, this, that, find all the open channels. Okay,
exactly.
That's like 5 years worth of work, right? But is there anything from your exploration that you could say to Intel and say, hey, SGX has all these hidden assumptions, right? It's all these channels. Did you learn anything that you could say, hey, this would really help us if we modified the hardware in some really specific way, or is it basically a free-for-all right now to figure out if it even is possible?
Could you say that again?
So really specifically, you've explored this really nice, rich environment and found these channels. Could Intel modify the way they do interrupt handling or the assumptions they have about the OS? Could they have a little security kernel? Could they hide more state? So what could they do to modify the actual implementation of SGX to close some of these channels off?
Oh, I see. We can maybe Intel modify the EExit behaviors not to leak the enclave context, but it is used to deliver some parameter between the enclave and untrusted app. So maybe we can mitigate this behavior, but I don't know about that. How can we mitigate this currently?
Thanks.
Yeah.
One last question.
Hi, Mihai from Visa Research. Very nice talk. One question, you mentioned software mitigations. I'm wondering whether existing mitigations like CFI would work as is, or do they need to be adjusted for HGX environment?
I think we can apply traditional software mechanisms, but that's actually the key takeaway from our work. So we want to say that we need to care about software vulnerability inside the enclave. So, yeah.
Thanks.
Thank you. Okay.